All right, we're finally starting a new chapter in our book. So that last one was a long one. It covered a lot of material. In Chapter 2, what we're going to look at is polynomial and rational functions. And this first section, 2.1, is on quadratic functions, and quadratics are a special type of polynomial function. Now, at this point then, you should know everything there is to know about quadratics. So this PowerPoint is going to be a review. Maybe there's some stuff you don't quite remember. If not, this is the time to get it cemented in your mind because everything builds off of this. So it's very important that you understand this inside and out. So take good notes, ask good questions in class, and make sure that you know what's going on when it comes to quadratics. Here I just have some examples of quadratics. And you should be able to recognize then just at a glance of an equation that it is a quadratic. So we are looking for that variable that's raised to the second power. It doesn't necessarily have to be the first term. It can be anywhere in there. Now take a look at this fifth one here. I have x plus 1 times x minus 2, and I don't see an x squared. But you should see that, when I multiply two linear factors together, I am going to get a quadratic. So here we have x squared plus x minus x minus 2. The first 5 here are quadratic in x, so that means our parabolas are going to open up or down. And our last one is quadratic in y, so this is the parabola that's a little bit lazy, and so if it's quadratic in y, it opens to the right or to the left. So it looks like one of these guys. Okay, so all of these are examples of quadratics. Now remember that our parent function is just y is equal to x squared. So what we're going to look at first of all is just what happens to that parent function when we put a value in front of the x other than 1, because we know if it's a 1, then it's our parent function. But if the a is a positive number, so a positive half, positive 2/3, positive 7, positive 5. If it's a positive number, then we know that the parabola opens up. But if the a is a negative number, so the way we say a negative number is it's less than 0, then we know that it opens down. And keep in mind, the a cannot ever equal 0, because if a is equal to 0, then you've taken out your quadratic term. The x squared is gone. So it either has to be greater than 0 or less than 0. All right, we can, with that value of the a then, not only does it affect its opening, whether it's up or down, but also whether you're stretching or shrinking it, but it always has to deal with a vertical stretch or shrink when it's the a, the number in front of the x squared. So the x squared then is your quadratic, because that's what makes that whole equation a quadratic. If we didn't have an x squared in there, then we'd, and it was just an x and a constant, then we're back to a linear function. All right, to shrink it vertically means that we're compressing it down, so we've got to take that y value times something smaller than 1. So if our a is less than 1, greater than 0, okay? Well, it's still going to shrink it if, like it's a negative half, so we are talking about like the absolute value of it. So if it's a negative half, it's still going to shrink it, but it's going to flip it upside down in addition to that. Okay, and to stretch it vertically then, the value of the a has to be greater than 1. If we want to do both, if we want to stretch it vertically and we want to flip it upside down, then the absolute value of the a. So that negative doesn't change whether it's a stretch or a shrink, right? And if we're doing that, if we're changing the value of a, then we're changing the shape of the curve. of the curve. So therefore, it is a non-rigid transformation. Non-rigid. It doesn't look the same. It's stretched more, it's skinnier, it's shrunk more, it's wider, so it doesn't look the same. All right, now let's move on to another transformation, and this one happens inside the parentheses, and so I used an H here. So if inside the parentheses we see a number that's added or subtracted to the x, then we know that it has been shifted to the left or to the right. So let's take this one here. Let's say we have y is equal to x minus 3 quantity squared. Okay, and if we compare that graph to the parent function, and you can go ahead and graph that on your calculator if you want to look for sure, but what we're doing is we are moving it to the right for 3 units. To the right 3. So that minus there is to the right 3. So that's the one that's the opposite one. Anytime it's embedded inside the parentheses. Whereas if we see a plus in there, so let's say x plus 4 quantity squared, then this one is moved to the left 4 units. Okay? But notice I haven't put anything in front here. My leading coefficient here, or the number out to the front here, the a value that we just talked about is 1. So I'm not changing the shape of it. So if I don't change the shape of it, then it is a rigid transformation. And if we, if we just slide it, then it will be a rigid. We can also take a value and just add it or subtract it at the end of the quadratic. So the way it compares to our parent function is we're taking the value of it, we're still squaring the x first of all, and then after that we're adding a k to it, or adding a negative k to it. So if the k is a positive number, then we are shifting it up. And if the k is a negative number, then we're taking the whole curve and we are moving it down that specified amount. Okay? So y is equal to x squared plus 7 is up 7 units from the parent function. If we have y is equal to x squared minus 2, then we know it shifted down to from the parent function. Okay? So I haven't changed the a value yet. So, or on this one, so that's still a 1. So that means we're not changing the shape of it. We are just shifting it up or down. So that would be another example of a rigid transformation. If we take all of that information and we put it all together, we can refer to it as standard form of a quadratic. So standard form here, notice we see the a, and the a once again stretches or shrinks it. We see inside a number added or subtracted on, and that is your horizontal translation, so it's going to be left or right, and the plus k at the end is the vertical translation. Okay, so it's moving it up or down. So if I have the equation y is equal to 2 times the quantity x minus 3 quantity squared plus 2, actually let's not use a 2, let's use a 4 maybe. Okay, so if I look at this graph then, from our parent function, so from y is equal to x squared, the 2 is telling us that we're stretching it vertically. The minus 3 is telling us that we're shifting it to the right 3. And the plus 4 says up 4. So we're doing that all at the same time. Okay, so when you look at this, you can tell what the vertex of your parabola is. And your vertex is at the point HK. So on this particular parabola, the vertex is at positive 3, positive 4. Okay, so if you were drawing a graph of it, instead of the vertex being at the origin, you go to the right 3 and up 1, 2, 3, 4, and this is the vertex. And then we want to apply the vertical transformation, which is stretching it by 2. So instead of going over 1 and up 1, we go over 1 and up 2. And then to the left 1 and up 2. So here is what it would look like. So standard form is a very nice form to have it in if you have to graph, because when you graph a quadratic, we need to know, several points on it, but the key point is the vertex. And you can tell them where it's been translated, and then after we get that vertex, then we look to see, well, is it opening up? Is it opening down? Is it stretched? Is it shrunk? So if the parabola is not in standard form, we might want to get it there, especially if I ask you to graph it. So what we're going to do is take a look at these two. So these are not in standard form. So you notice you don't have a quantity squared there, so we can't find what the shifts are by looking at it like this. So we are going to complete the square. Okay, so I gave you two. I gave you one where the x value, the coefficient of the x squared is 1, so that's our a value. And then I gave you one where it's a half. Okay, so we're going to do both of these. Let's start with the first one. And to complete the square, so remember that means we have to have some quantity squared here. I have a leading coefficient of just 1, so I don't need to pull anything out. So I'm just going to put a open parenthesis, and I'm going to group the x squared with the x term. So I've got the quadratic term and the linear term in here. Then I'm going to leave a little bit of space and put the end parenthesis, and then that minus 3, I'm just going to ignore it for just a second. So we are concerned about what's inside the parenthesis here, and what do we have to add in order to make this a factorable quadratic such that it will factor into a quantity squared like this. Okay? Well, in order for that to happen, we take half of the coefficient of the x term, so the 6, and square it. Half of 6 is 3, squared is 9. Now let's take a look at that then. I told you that this would be able to factor like this. All right, so we're going to go ahead and factor it then. So we would get x. I hop over to that constant term, see it's a 9. So anytime you see a perfect square, then you want to try the square root, see if it works. Now, will that get us a middle term of 6x when we multiply it out? Well, we're taking x plus 3 times x plus 3. So your middle terms, where you multiply the out and the inner, you get a 3x and another 3x. So yes, indeed, that'll give us a 6. All right, so remember we took half of the 6 and squared it. That now changes the value of our quadratic, because I just added 9. Well, you can't just add 9 to something and then have it look the same. So I've got to counterbalance that. So out on the outside of the parentheses then, we're going to put a minus 9. Now that is okay, because 9 minus 9 is 0, and I can add 0 to anything and not affect it. So I want this to stay in factored form then, and all I have to do now is combine the negative 3 and the negative 9 at the end for minus 12. So that's all there is to that one. So now we have it in standard form. The a value is 1. The h is negative 3. The k is negative 12. And remember, the hk gives us the vertex. This parabola then has been shifted to the left 3 and down 12. But it has the same shape of our parent function, y is equal to x squared, because I haven't changed the value of a. So this one then is a rigid transformation, this particular one. All right, let's go back over to this other one where we have a 1/2 in front of the x squared. Well, this complicates things a little bit. So in order to complete the square, we want to have a leading coefficient of 1 inside of here. So anytime you have a leading coefficient other than 1, that has to be factored out. But I'm only concerned about the terms that are going to end up inside the parenthesis. And notice how in the last one we put that constant term at the end of the parenthesis. Well, we're going to do that same thing. So we're just going to put the plus 5 over here. Okay? I want to factor out then the 1/2 out of the first two terms. So if I factor out a 1/2, 1/2 x squared divided by 1/2 is just x squared. Now I've got that inside the parentheses anyway. I have a leading coefficient of 1, and that's what we want to be able to complete the square. I also have to factor it out of the x term. So we have a negative 2x divided by, we're factoring out a 1/2. So negative 2 divided by 1/2 is negative 4, and then the x. Okay, and I left just a little bit of room then. So since the 1/2 is on the outside, on the inside then, we are going to complete the square. So 1/2 of negative 4 is negative 2, squared is 4. So we want to add, let's see, let's grab green. We want to add 4 to this. Okay. By doing that, I'm changing the value of our quadratic. Don't want to do that. That's not a good thing. So we are going to then counterbalance what we added there. Well, in this case, when I actually put a plus 4 in there, but because it's inside the parentheses with the 2 on the outside, that means that 1/2 is going to have to be applied to that 4. So 1/2 of 4 is 2. So really what I did is I added 2 to that. So that means over here with the 5, I want to subtract 2. So I want to counterbalance that, because I can't just arbitrarily say, hey, I'm just going to add 3 to that parabola. That changes the parabola. So you can't do that. So you always have to balance it out. All right, now we take this then and we factor it. That 1/2 is essential on the outside because that tells us about the shape of that parabola. On the inside, we factor this because that middle term is a minus 4x and the constant term is plus 4. I need a negative 2 quantity squared. And we combine the 5 and the negative 2 for a positive 3. Now we've got it in standard form. You should be able to tell me then that the a value is a 1/2. You should be able to tell me then, or visualize that parabola with an a of 1/2. We are shrinking it by a 1/2, so it is wider than our parent function. The h value is positive 2. The k value is positive 3. So that means our vertex is at the point 2, 3. And so what's nice about standard form is that we get this information. It's easier to tell about the parabola from here than from here. Because look at, even the constant term has changed. So it's not necessarily being shifted up 5 here. It was only shifted up 3. Okay, so it's critical then to see the transformations, to put it in that standard form. Now let's say we want to find the x-intercepts. Well, I could be really nice and give you a quadratic that looks like this. It's already factored for us. Let's say we have x plus 1 times the quantity x minus 2. Anytime we find the x-intercepts, not just on quadratics, but any functions, to get the x-intercepts, we plug in 0 for y. So I want to know, well, if I'm going to multiply these two guys together and I want to get a 0, the only way that's going to happen is if one of them is 0. So x plus 1 could equal 0, or x minus 2 could equal 0. In which case, x could be a -1, y could, x, where did I get that y? X could equal +2. Those are our x-intercepts. So this parabola is crossing the x-axis at -1 and at 2. Okay, so those are the x-intercepts. As points, it would be -1, 0, and also again at the point 2, 0. Come on. Those are the x-intercepts. Okay, so you could get one like that, or I could be ornery and say, hey, why don't you take this guy plus 5x plus 6. I want you to find the x-intercepts of that guy. Well, same thing. We substitute in 0 for the y, but it's not in factored form, so that means I'm going to have to work a little bit harder. So if you can factor it, if you recognize it, that's the way to go. So let's try it. X squared, well, we'd have to have an x and an x. Factors of 6, 1 and 6, 2 and 3. We have both negatives, both positive. But because I want a positive here and a positive here, both positive. So we'll take the 2 and the 3. Plus 2 plus 3. So that means then that our x-intercepts are at -2 and also -3. So this parabola is also crossing the x-axis twice. Now, that doesn't mean everyone does. Not every parabola. So here's an example of one that crosses twice. Here's one that only maybe crosses one time. Or it could be that you have a parabola that doesn't cross at all. Okay? So if when you go to factor it, it doesn't factor at all, then you have to use the quadratic formula. And we will practice that in class. Now let's do this one. If we write the equation of a quadratic, then we have to know the a value and the h and the k. So we're starting off with our standard form. And the reason I want to use this form is because the vertex was given. So I already know the h and the k. So we're going to substitute that in. So x minus -4, so that'll become a +4. And then plus k, so it's a +1 at the end. All right, so I've got 2 of the 3. So that was not too bad. Now we just have to figure out what the a is. Well, in order to figure the a, solve for the a, I have to know both an x and a y. And that's what this guy is for. Okay, so we're going to substitute him in for the x and the y. So the y is 2. At the same time, the x is 3. So let's put the rest of the information in there. So we need the 3 plus 4 squared plus 1. The a is what I'm looking for. Now you can see that a is the only variable in that equation, so we can solve it for a. So we're going to subtract 1 from both sides. We're going to add 3 and 4 together, get 7, and then square it. And then we're going to divide by that. 49. Okay. So let's check that then. That wasn't what I originally intended. Let's see. Did I make a mistake? Okay, I want to go look at the vertex. The vertex is at -4. Oh, nope, I didn't. So -4, 1. When I did this in my head, I was thinking +4, -1. And so now it's going through the point over here, 3, 1, 2, 3, 1, 2. So yes, indeed, here's the vertex, so that parabola is going to be very wide. So 1/49. Oh boy, that's not what I meant, but that still works. So here is our equation then written in standard form. 1/49 times the quantity x plus 4 quantity squared plus the k. That's the equation. Now, some of you, when you write an equation, you're thinking you have to fill in everything. Don't put in an x and a y, because the x and y could be any point on that parabola. And yes, these two both happen to be points on it, but you don't want to substitute them in. You need to keep that x and the y there. All right, I think that's all we're going to do for right now. So I appreciate you taking good notes. Hopefully it all made sense. Questions, you're going to ask me first thing when you come back to class. All right, see you then.